Hello, you absolute legends. Let's discuss this unique relationship between the equilibrium constant, capital G, and free Gibbs energy, capital G. In phase one, we'll talk about this relationship, and in phase two, we'll talk about how we can determine delta H enthalpy or entropy S by a substitution of equations. It's a lot easier than it sounds. Capital K, the equilibrium constant in phase one, simply defined. K is the concentration or molarity of products divided by reactants. Very simplistic way to write that equation right there. There's things I'm leaving out, but it's products divided by reactants, molarities or concentrations. Standard equation for calculating G. This is very common, something you see out of the lab book here. Gibbs energy, H, enthalpy, or the energy in the bonds and movement, temperature, and entropy, S, the movement of the energy and the movement of the molecules. Excuse me here. These are both equations that can be used to judge the spontaneity, the forward or backward reaction. Now, what's really fascinating is that when man's predictions of Mother Nature really are based in foundation and solidness is when these equations can be combined. And one of the ways these equations can be combined is in this problem here. We have negative RT times lnk. Whoa, a lot of stuff just happened right here. Delta G, G, Gibbs free energy, and K. Those are the two big things I want you to see right now in this formula. That G and K are relatable to each other. And they are relatable in terms of the gas constant R, the temperature T, and the natural log function on capital K here. To explain the gas constant, the movement of molecules of gases and liquids are similar and proportional to each other. And that is why we can that is a physical explanation of how this mathematical term can be used in here. The gas constant has a temperature term in it, so multiplied by T cancels out the terms and the limits there, our units come out. This formula right here is where we enter into phase two, where we can solve for H and S, the enthalpy and entropy. A substitution of equations is done with this and this. Take a moment and note that they are both set up to be equal to G. G equals this stuff. G equals this stuff. Therefore, we can say this stuff is equal to this stuff. At this point, I'm not concerned that you understand what all this stuff is. What I want you to see here is that these things are equal to each other because they're both equal to G. This is the first thing I want you to see. Second thing I want you to note here is that when I break this down or tear this down, my goal is to get this into a y equals mx plus b format. Now, let me go ahead and do that. It's going to look and go a lot simpler because I already know what I'm looking for here. But if I didn't know how to do this and I was asked to do this, I would be going through a bunch of paper, just trying to solve and rearrange the stuff to make it look like y equals mx plus b. Here's one way it can look like y equals mx plus b. We divide both sides of the equation by RT, negative RT. Dividing by RT, like terms cancel, and here I separated out some things here. What I'm gonna do is I'm just gonna clean up some of my plus and minus signs. I'm going to clean this up too, just so everything looks nice, because So negative, I'm going to clean up some of my temperatures. These terms cancel, so I'm also going to cancel out those right there. All right, great. This looks very much more like y equals mx plus b. Feeling me? Let's clean this term up some more right here, okay? Now we want this to look like y equals mx plus b. Okay, I can see straight up that the y is the ln k. And the b is s divided by r. Remember, s is our entropy term, and r is our gas constant. Now, here we have three terms, h, r, and t, and we want them to, in some way, they got to come up with a combination of m and x, okay? M is negative hr. That is my m, or slope of the line. And then x is 1 over t. Looks funny that's 1 over t, but t is in the denominator here, so it's still mathematically correct, but it does look a little funny here. Here we see parceled out what you can plug into a chart to get a straight line fit. The y term, ln of k, you know k, so you can just boop, 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 beep, bop, boop, bop into that your calculator, ln of k. X is 1 over t. You know t. It was room, depending on the experiment, it was room temperature or hot or cold, but you know t. So you know the y and you know the x. That should give you a data point for room temperature. You can do another data point for higher temperature, another data point for lower temperature. These should come out in a straight line. I'm just showing a positive slope, but I'm just putting dots together right here. But this is what Excel does. You plug in your y's and your x's into Excel, and it should shoot out a scatter plot showing it right here. And then Excel tells you what the equation of the best fit line is. And Excel gives you numbers though. It gives you something that looks like this. It says y equals 3x plus 4.5. This is what Excel will give you. And this is what you have written on your paper. And your job is to play match. The computer doesn't know what y is. We know that y is ln of k. The computer doesn't know what this 3 is. We know that 3 equals negative h divided by r. That's foundational. We know that 3 equals h divided by r. That negative sign in there. We always know r because of the gas constant. So now we can solve for h. Yes. The computer knows that the y-intercept is 4.5. We know that the y-intercept is entropy S divided by the gas constant. We always know the gas constant, so we can plug that in there and solve for S. I hope this helps. Thank you.